All right, ladies and gentlemen, welcome back to the Simpkins Physics Corner. Today it's uniform circular motion, and specifically we're going to investigate this idea of what is the centripetal force, right? This is an important idea because depending on the situation, many different specific forces such as friction, normal force, tension, and gravity can function as the centripetal force. And that idea turns out to be rather mathematically useful when we go to solve for things that we're looking for. So I put together this big four sheet here for you guys. To give you an idea of what types of problems you might see. So for the first one, for example, it says write an equation for the minimum coefficient of friction. All right, that's mu for those of you that have been with us here. That's mu for any gravitron with vertical walls to keep riders from sliding down the walls. So this is a classic physics problem. Your teachers love giving you this one, so do I. All right, the gravitron, if you're not familiar with this ride, it's basically like a giant spinny ride. You're inside this large, I don't want to say cylinder, if you will, and the riders ride on the outside and they spin you up. And when they spin you up, you feel like you're being pressed towards the wall. Now we know that's not a force, that would be centrifugal force, which is not a thing. It's just that your body wants to fly tangent, right, because of the law of inertia, but the force of the wall, the normal force, pushes you back inside. So the first thing you want to do for any circular motion problem is understanding the forces that are applied to the object. So here, of course, we're going to have the force of gravity down. And if you're not sliding down the wall, it's because you're sticking to it. It's because of the force of friction. If I left the free body diagram just like this, that would indicate a downward acceleration. The unbalanced force would cause the acceleration. But we do have a force, and that force is friction. So our last unit was dynamics, and the big idea was sigma F equals ma. And for this unit, that idea remains. Right? It's just that now it's the net centripetal force causes a mass to centripetally accelerate or experience centripetal acceleration. And so we're still going to write that expression in two dimensions. If you look at the first dimension, the vertical dimension, we have identified that we are trying to be in equilibrium here, right? So that means that the force of friction must be equal to the force of gravity acting on the rider. And we also know that we're moving in a circle in this horizontal plane, and so that means that the centripetal force is the normal force. All right, that's what is the centripetal force. Now, from F equals ma and from our equation sheet AC equals V squared over R, we know that we can take this, V squared over R, and plug it in there for our generic equation for centripetal force, which would substitute in as mv squared over R. If you take a quick look, we went from F equals ma and A equals V squared over R, so therefore F equals mv squared over R for that substitution. Now, in the other direction, we're looking for the mu, keep in mind. Well, let's go ahead and explode these equations. What I'd like to say is, can you substitute anything in for them? And so for the force of friction, of course, we can do mu times Fn. And for the force of gravity, that's going to be equal to mg. So you see we have these two separate expressions. And the question is asking us to solve for mu, or to write an expression for mu. So what we could do here is just say mu equals, and that's going to be equal to mg divided by the normal force. And then this is why the class sometimes gets dubbed AP substitution, is because we're going to substitute this normal force expression, mv squared over r, and we're going to drop that right here into the mu expression that we have. You have two equations with the same unknown. You can solve for that unknown in one equation and plug it into the other equation. Substitution, that's exactly what we're doing here. And so it's a little funky with the fraction. I'll show you how this works. But that means that mu is going to be equal to mg divided by mv squared over r. Okay. Now, if you're getting a little bit of a headache looking at that algebraically, remember that dividing by a fraction is the same as multiplying by its reciprocal. In other words, mg times r over mv squared. Okay, and that kind of helps you figure out where that r goes. You notice that the m's cancel, and so our final expression here, mu, is equal to gr over v squared. All right, so that is our generic expression for any gravitron problem where it's a vertical wall and the friction is the thing keeping you from falling down. So for my students, you can go ahead and try this out if you want. 22.27 revs per minute, and I gave you 4 meters, and you should find the answer is 0.45. Just a couple of other things to keep in mind as you do this particular one is that revs per minute is not a standard unit. You're going to want to take that into revolutions per second, which would be the unit for frequency. Then you want to put that into radians per second because that's an easy thing to convert it to. And then using the equation V equals omega r, you can solve for your velocity, which is in our expression here, mu equals gr over v squared. I'm going to pause after this one and break this video into smaller chunks because I have to go to lunch duty soon. I love chilling in the cafeteria when carrots are being thrown. This is Mr. Simpkins with Simpkins Physics Corner for one of the big four.